Hi all, in this video our standard is the difference quotient. We've got two objectives, calculating the average rate of change over an interval and simplifying the difference quotient. We start with calculating the average rate of change over an interval, and a note, when a function isn't linear, we can't calculate its slope per se, but we can still look at how the function is changing. To find the average rate of change, or arc, over an interval from a to b, we find the slope of the secant line, one that intersects a graph at 2 points. The line passing through are points a, comma, f of a, and b, comma, f of b. And we can look at the graph to make those make sense and line up with what you already know about slopes. We have our points a and b marked with their y values, f of a and f of b. We can think of a as x sub 1, the first x coordinate, and f of a then as its function value, or y coordinate, so y sub 1, and b as x sub 2, with f of b then being y sub 2. So our slope of that green secant line connecting the points, we've got m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. For our notation with our a's and b's, that makes our arc f of b minus f of a over b minus a. So we're just looking for the a and b values that are given to us, right? We're looking for this interval of values, or two x's and their corresponding y's. We're still just looking at points. And so this average rate of change is just going to be a units of rise per, that's the over, right, units of run. So we still have to go back to units. We still talk about it the same way we talk about a slope, but it's our average change. So usually we'd try and make that denominator a 1, and we'd say per, like, dollars per hour or miles per gallon or something. So we can track this average change over a time period. Okay, so note here, the arc of a linear function is just the slope of the line. If we're computing a slope between 2 points, any 2 points we take on the line will create the line that passes through there, and thus the arc will be the same as the slope. So let's do one that's not linear. Number 1, calculate the average rate of change of f of x equals x squared from, for a, we're going to go from x equals 0 to x equals 2. So we can look at our points. There's 0, over here's 2. F of 0 would just be 0. F of 2 up here is 4, but we can write it down just to make sure we know what our a's and b's are. A is 0. That means f of a is just f of 0, which we can see from the graph is down there at 0. And b for this one is 2. So f of b is f of 2, which we can see is 4. Or you could sub into the function, right? F of 2 would be 2 squared, which is 4. So we want to know what that function is, but we also have the graph here we can read from. So our average rate of change for this interval from 0 to 2, we can write it a couple times just to get used to it. This f of b minus f of a over b minus a would be 4 minus 0 over 2 minus 0, which is a 4 over 2, or 2. All right, and if we did look at the secant line there, let's see if I can draw a nice-ish. We can see our slope there. We are going up 2 over 1, up 2 over 1. So we can see that line has a slope of 2, or our average rate of change over that interval is 2. For every 1 unit we go over, we go 2 units up. All right, for b, we're going from -1 to 2. So here our a is -1, which gives us an f of -1, or f of a, that is 1. And b was the same. B is 2, so f of b, or f of 2, was 4 for us. So our average rate of change, we can write one more time, f of b minus f of a over b minus a, just to get used to it. We get a 4 minus 1 over 2 minus -1. That minus a negative becomes a plus 1, which gives us a 3 over 3, or 1. And so if we look at our line that would connect those 2 points, we see that average rate of change of 1, right? Up 1 over 1, up 1 over 1, up 1 over 1. 1 to connect the points. And for C, we're going from -2 to 2. You might be able to see what's happening here. But if A is -2, our f of -2, or f of A, is -2 squared, or 4. And we already know B as 2 gives us an f of 2 of 4. So our average rate of change there is just 4 minus 4 over 2 minus -2, which becomes, of course, 2 plus 2. So our numerator goes to 0. Our denominator is a 4, and 0 divided into 4 pieces is still 0. And we can see for that one, we'd have a horizontal line connecting those 2 points, which does have a slope of 0. So our average change there from -2 to 2 would be 0, even though we know a lot of stuff happened on the function. We're just looking for that average change over the interval. All right, our second objective is to simplify the difference quotient. Note here, if we label our interval x to x plus h, we get a secant line from x comma f of x and x plus h comma f of x plus h. So here a we can call x, b we can call x plus h. H is just representing the distance between those points. So this distance is h. And when we look up then, f of a would now be f of x, and f of b would be f of x plus h. We're just evaluating the function at that second x value, or that second value for the interval. So if we use our arc here, which was f of b minus f of a over b minus a, it can be rewritten as, with these new points, f of x plus h minus f of x over x plus h minus x, which gives us an f of x plus h minus f of x all over h. So that's our average rate of change. What we want to kind of lead into, so a little bit of maybe bonus, but also just so you've seen the difference between these two things before, is what happens as that distance h becomes 0, or as these get really, really close to the same point. So kind of that idea we talked about with the limit of zooming in on a point. And you'll see that coming back in a second here. What we're looking for in calculus is the slope of the tangent line. And hopefully it'll make these problems make a little more sense. But we're looking for a slope of a tangent line. And so all we have to add to this, what makes it an ERC, or an instantaneous rate of change, is that limit. So our limit as h approaches 0, right, as that value between the x and the x plus h points goes to almost nothing as we zoom in around that point at x, the same piece goes aside, that same expression, f of x plus h minus f of x over h. And so again, we're not doing limits algebraically, but we almost are. You're going to do the same work here that you do in calculus. You'll just get one extra step in calculus that kind of motivates why we're doing the work we're doing here. So I wanted to at least preview that. And so our difference between an average rate of change is that we're over some interval from a to b, or x to x plus h. When we move into calculus, we're going to be looking for that instantaneous rate of change, or what's happening at a single moment in time instead of over some interval of time. And so we're looking at what happens as h becomes 0, or as those points kind of merge together. And so our whole goal when simplifying difference quotients is to get rid of the h in the denominator that's causing us a problem, because we know we can't divide by 0. So hopefully that helps a little, and I'll show you it's one tiny extra step at the end of each of the problems you'll do in the pre-calc. So with these values, we have the expression f of x plus h minus f of x all over h. So that's all we want in that blank. That's called the difference quotient. Right, it's a quotient of differences, right, the change in y over change in x still, and is used to calculate derivatives, or what we call instantaneous rates of change in calculus. So we're going to construct and simplify difference quotients for a few problems. That's all we've got left. We'll take you through the gamut of kind of types we have to do, which also ties into the previous notes. So construct and simplify the difference quotient here of f of x equals x squared. Our first step for a difference quotient is always to determine what f of x plus h is. And what we have been trying to get you used to is that anything inside that function is just substituted everywhere you have an x in your function, right? That x is just a placeholder. So here, f of x plus h is going to be x plus h quantity squared. When we square that binomial, we know we get an x squared plus 2xh plus h squared. Write out the distribution or foiling if you need to. Don't forget that 2xh, it's very important. And then we can do our difference quotient. So write it a few times to get used to it. dq equals f of x plus h minus f of x all over h. And then it's just a substitution. So we have that f of x plus h over there. We try some color, let's stick with red. This whole thing is our f of x plus h, so we can throw in an x squared plus 2xh plus h squared. And then we're going to subtract off our function f of x. Let's go blue. So x squared is what goes in there. It's a single term, so I don't really need the parentheses here, but once you're substituting again, you want to get used to those parentheses so we don't miss some distribution with the minus. And always over h. Then we can simplify. I'll pretend I'm doing that distribution first to get rid of the minus. So a minus x squared, there's only one term. So the negative goes into it. So we have x squared plus 2xh plus h squared minus x squared over h. And when we are doing these problems, what we're looking for is kind of a two-step process. We want all of the non-h terms in the numerator to go away. So x squared minus x squared is a 0. And we get a 2xh plus h squared all over h. And then we want to factor out an h. Right, our goal is to get rid of that h in the denominator. That would become 0 if we looked at what happened as the distance between those 2 points became 0. So if we factor out the h for the numerator, we get a 2x plus h left inside all over h. We divide out those common factors of h. And we're left with, for our dq, a 2x plus h. So the one step that we could do in the calc would be to take the limit as h goes to 0 of this difference quotient. And you don't have to do this, but just wanted you to kind of see what you're leading into. We take the limit as h goes to 0, and so we're left with just 2x, right? We want to look at what happens if h is 0. And so again, that's that motivation for having to get rid of that h in the denominator. So when h becomes 0, we don't have a division by 0. I'll show it to you for the bigger ones as well. It's not too much to hopefully write and confuse you. So for 3, we've got construct and simplify the difference quotient of f of x equals 3x squared minus 5x plus 4. So again, we want to find f of x plus h first. For this one, we have 2 x's in our function, so both need to be substituted for that x plus h. I'll do this in 2 steps. For the first one, I'm just going to do that squaring. So x squared plus 2xh plus h squared. After that, 3 minus 5 times x plus h still plus 4. And then we can do all our distribution. This would give us a 3x squared plus 6xh plus 3h squared. And the minus 5's got to go in as well. So a minus 5x minus 5h plus 4. And so that whole thing is our f of x plus h. So when we substitute into our difference quotient, where we want f of x plus h minus f of x all over h, we get our whole expression we just simplified for f of x plus h, the 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 4. And we're going to subtract off our original function. F of x was a 3x squared minus 5x plus 4. So when we do that distribution, we want to keep those parentheses, and then all over h. To simplify, we can rewrite most of the numerator, 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 4, and then do our distribution, minus 3x squared plus 5x minus 4 all over h. And so hopefully we can see our like terms there. Right, we've got a 3x squared and a minus 3x squared will go to 0. A minus 5x and positive 5x will go to 0. And then the plus 4 and a minus 4 will go to 0. And that's us getting rid of all those terms without an h. So we're on the right track. We're left with a 6xh plus 3h squared minus 5h over h. So all those terms have an h in them in the numerator, which means we can factor it out and write it as h times our quantity, 6x plus 3h minus 5 all over h. When we divide out those common factors of h now to get rid of that h in the denominator, we find that our difference quotient is 6x plus 3h minus 5. And again, not for us, but for the calc, we'd have one last step, looking at what happens as h becomes 0 for that difference quotient. If I sub in 0 for h, I'd get a 6x minus 5. All right, two more. We've got some that relate now to the last sections, the simplifying radicals and the complex fractions. So for 4, we're going to construct and simplify the difference quotient of f of x equals the square root of 3x plus 4. That would give us an f of x plus h of the square root of 3 times the quantity x plus h plus 4. And if we simplify that underneath the square root, we get a 3x plus 3h plus 4. So substituting into our difference quotient, we again want to look at f of x plus h minus f of x all over h. Our f of x plus h, that whole expression now is getting substituted in. So we get a square root of 3x plus 3h plus 4 minus our original function, f of x, is the square root of 3x plus 4. Right, it's all contained in that radical already, so we don't need more parentheses. Right, the radical's already grouping them together, and then divided by h. So this takes us back to when we were rationalizing a radical expression, and we needed to multiply by the conjugate, right, to rationalize the numerator here. And we can do that conjugate on the next line to make it nice and big. So we've got the square root of 3x plus 3h plus 4 minus the square root of 3x plus 4 all over h. And then we're going to multiply by our square root of 3x plus 3h plus 4 plus, now in the middle, right, our opposite signs for the conjugate there, our square root of 3x plus 4 all over the same thing. Right, we can only multiply by 1 to change how it looks or to rationalize without changing the value. So square root of 3x plus 3h plus 4 plus our square root of 3x plus 4. And when we multiply out now, we know we just get the radicand from the first term. So we get a 3x plus 3h plus 4, and then minus the radicand for the second term, since they were both radicals. When we square them, we just get that expression inside, or that radicand out, the 3x plus 4 over here. All over the denominator, we want to keep that factor of h that we know we're trying to get rid of, and then we'll multiply by that whole conjugate, 3x plus 3h plus 4, plus the 3x plus 4 under the second radical. All right, and so we can distribute in the numerator. We get the 3x plus 3h plus 4 minus 3x minus 4 as we distribute that minus 1 through. All over our denominator stays the same. We want to leave that factor of h times our square roots, 3x plus 3h plus 4 plus the square root of 3x plus 4. In the numerator, we can see the 3x and minus 3x would go to 0, the positive 4 and minus 4 go to 0. And we're left in that numerator with just a 3h term over our denominator h times our quantity, square root 3x plus 3h plus 4, plus square root of 3x plus 4. Now that we have that factor of h in numerator and denominator, we can divide it out. And we end up with a difference quotient here of 3 over our square root of 3x plus 3h plus 4 plus our square root of 3x plus 4. Our calculus preview, we take the limit as h becomes 0 of this difference quotient, and we would get a 3 over square root of 3x plus 4 plus the square root of 3x plus 4, which we can reduce to 3 over 2 times that square root of 3x plus 4. Right? We'd have like terms down there. One 3x plus 4 plus another one would give us 2 of them. All right, one more with the complex fraction here. We want to construct and simplify the difference quotient of f of x equals minus 2 over x minus 1. And just to make it easier for you, we're going to rewrite it with that negative in the numerator. So it's a minus 2 divided by x minus 1. Our f of x plus h then becomes negative 2 over x plus h minus 1. Right, there was nothing in front, so I didn't use parentheses, but you could and then write another step. But we're just replacing x with x plus h, and then we can take it into our difference quotient. So our dq, f of x plus h minus f of x all over h becomes, we'll take that whole expression now, for f of x plus h, the minus 2 over x plus h minus 1, and subtract off our whole original function, right, with that minus 2 over x minus 1. Guess I didn't use my red there, but I think you can see what's happening now, all over h. And for the complex fractions, we wanted to multiply by the LCD. So we can take it to the next line again to make it nice and big. We've got a negative 2 over x plus h minus 1 minus a negative 2 over x minus 1. And I might even change those to positive there for you. Minus a negative becomes a positive, so we don't have to worry as much about that distribution. All over h. And then we're going to multiply by our LCD. We had fractions of, or with, x plus h minus 1 and x minus 1 in their denominators. So we're going to use those, or that product, to make our LCD. We multiply it to the whole numerator and whole denominator of our complex fraction to clear out all the denominators as we multiply through. So we're distributing through the first and second terms up here in the numerator. When we do that, our first term turns into a negative 2 times x minus 1, as the x plus h minus 1 is divided out. And when we go into the second term, we get a plus 2 times our quantity, x plus h minus 1, as those x minus 1s are divided out. And our denominator, we're going to keep all three factors, so h is there, times x plus h minus 1 times x minus 1. Again, we want to keep that factor of h. Our goal is to get rid of it, so our denominator doesn't become 0. And then we want to distribute to keep going and simplify. So a minus 2x plus 2. We distribute in that negative 2 to the x minus 1, plus 2x, 2h, plus 2h, and minus 2. All right, all over our same denominator, h, x plus h minus 1 times x minus 1. We can see our like terms, minus 2x and 2x go into 0, positive 2, negative 2 go into 0. So our numerator, we're left with just a 2h over h times x plus h minus 1 times x minus 1. We can see those factors of h now, right? H is being multiplied by the whole numerator and whole denominator, so we can divide it out. And we're left with a 2 over quantity x plus h minus 1 times x minus 1 for our difference quotient. If we did look at that one last step one more time for the calc, we're looking at our limit, or we're looking at what happens as h becomes 0 for that difference quotient. And we'd get a 2 over, if h is 0, just an x minus 1 times x minus 1, or 2 over x minus 1 squared. So let's see if we got room to just put a quick summary here. So maybe not steps for the whole process, but at least kind of what we're looking for as we go through to tell us we're on the right track. We want to eliminate all terms generally in the numerator without h. Right, and the whole point of that was to factor out that h that we had left in all the other terms, and then divide out our factor of h from the denominator. All right, so if we get rid of all the terms without an h, we can then factor out an h and divide out the h in the denominator. That would cause a problem. Our third step would be the calc. It's why we're doing the first two. It's why we have to get rid of that h and why we know we're on the right track if we do. We would take the limit as h goes to 0 of that difference quotient. So hop to the ticket, ask questions if you got them.